Hi, this is Sai Potana, founder at Embedded Systems AI LLC. In this video, we're going to look at one of the most important security events in modern computing history, Spectre and Meltdown. These vulnerabilities fundamentally changed how we think about CPU security. Before 2018, the industry largely trusted hardware isolation boundaries. After Spectre and Meltdown, there was a realization that modern processors themselves could leak secrets through performance optimizations. This was not just a software bug, it was a flaw in the interaction between CPU microarchitecture, operating system, compilers, browsers, virtualization, and cloud infrastructure. Let's start with Spectre. Modern CPUs try to improve performance using speculative execution. The processor predicts future instructions and executes them ahead of time before it knows whether they are actually needed. Normally, if the prediction is wrong, the CPU rolls back the architectural state. However, the microarchitectural side effects remain, especially changes inside caches, branch predictors, and timing behavior. An attacker can intentionally mistrain the branch predictor, force speculative execution down a malicious path, and then measure cache timing differences to reconstruct secret data. So even though the CPU eventually discards the wrong execution path, the cache has already leaked the information. Meltdown is slightly different and even more dangerous in some systems. Here the CPU speculatively accesses privileged kernel memory before permission checks complete. Architecturally, the access is denied later, but transiently the secret data already entered CPU structures such as registers and caches. The attacker cannot directly read the forbidden memory, but they can infer the data using timing-based side channels. The key insight is the permission check happens too late relative to speculative execution. These attacks showed that isolation boundaries were no longer purely architectural. The leakage occurred through hidden CPU behaviors, cache timing, speculative pipelines, reorder buffers, branch predictors, and transient execution paths. Performance optimizations unintentionally became covert communication channels. Spectre was extremely difficult to fix because it exploited fundamental CPU behavior. The industry responded with multiple layers of defense. Fence instructions such as L-fence were introduced to stop speculation across sensitive boundaries. Red pollines were developed to protect indirect branch prediction. Speculation barriers and predictor flushing reduced leakage between contexts. Microcode updates modified CPU behavior internally, and hardware vendors began redesigning prediction engines and speculative pipelines. Meltdown required stronger separation between user and kernel memory. The biggest operating system mitigation was KPTI, kernel page table isolation. Before Meltdown, user processes could still map portions of kernel memory for performance reasons. KPTI separated user and kernel page tables entirely. This dramatically reduced the attack surface but introduced additional page table switches and TLB overload. Additional defenses included microcode updates, hardened memory copy routines, stricter permission checks, and more minimal kernel mappings. One of the major lessons from Spectre and Meltdown was that no single mitigation is sufficient. Security became a cross-layer responsibility. Hardware, firmware, operating system, compilers, hypervisors, browsers, and applications all had to cooperate. These mitigations introduced real performance costs. Some workloads experienced 5% to 30% slowdowns, particularly in system call heavy applications, virtualization, storage, networking, and cloud environments. The industry had to balance performance against security. This event triggered one of the largest coordinated security responses in computing history. CPU vendors, Linux maintainers, Microsoft, browser vendors, cloud providers, compiler teams, and virtualization platforms all released emergency patches simultaneously. CPU vendors redesigned speculative execution logic. New architectural controls were added, like IBRS, STIBP, SSBD, enhanced branch isolation, safer predictor partitioning, and improved speculative tracking. Modern CPUs now include security-aware speculation mechanisms directly in hardware. The CPU design philosophy shifted towards secure by design. Operating systems underwent major redesigns. Linux added KPTI, red pollines, speculative barriers, CPU state flushing, and new mitigation syscalls. Kernel development became significantly more complex because mitigation paths had to account for multiple processor generations and threat models. In multi-tenant cloud systems, one customer's VM could potentially infer data from another tenant through shared CPU resources. This forced stronger VM isolation, tighter placement policies, disabling hyperthreading in some deployments, and constant microcode rollout coordination. Cloud security became deeply tied to microarchitectural behavior. Hypervisors required extensive modifications. VM exits and entries became more expensive because mitigation state had to be flushed or partitioned. New virtualization controls were introduced. VM enter protections, VM exit hardening, TLB isolation, and stronger guest separation. Virtualization performance tuning fundamentally changed after 2018. Compilers became part of the security boundary too. Compiler toolchains introduced red polline generation, speculative safe code patterns, hardened bound checks, safer inlining strategies, and speculative barriers. Security-aware code generation became a first-class compiler optimization goal. Browsers were among the most vulnerable applications because JavaScript could exploit timing channels. Browser vendors responded with stricter site isolation, process per origin architectures, reduced timer precisions, stronger sandbox separation, and more aggressive memory isolation. Modern browser security models were heavily reshaped by Spectre. In January 2018, researchers publicly disclosed Spectre and Meltdown after coordinated vendor notifications. The vulnerabilities were found across multiple processor families: Intel, AMD, and ARM. Operating systems, firmware, and hypervisors rapidly deployed mitigations. At the same time, researchers discovered additional speculative execution variants: Foreshadow, Zombie Load, RIDL, Red Bleed, Zen Bleed, and many others. Today, speculative execution security remains an active field. Modern CPUs continue evolving to balance performance, power efficiency, and security isolation. Security is now considered a fundamental architectural design constraint. Spectre and Meltdown changed computing permanently. They taught the industry that hardware cannot always be blindly trusted. Performance optimizations can introduce hidden attack surfaces, and security must be enforced across the entire computing stack. The future of computing is no longer just about speed. It's about secure performance.